On the morning of February 15, 1942, the largest British military surrender in history was taking place on the island of Singapore. 80,000 troops laid down their arms before a Japanese force half their size. Churchill called it the worst disaster in British military history. The world watched in shock as the fortress that was supposed to hold the Pacific fell in a week. But the catastrophe that mattered most to the American war effort was not the surrender. It was what the Japanese now controlled, the rubber plantations. Malaya, the Dutch East Indies, French Indochina, Thailand, Burma. In the space of 3 months, Japan had seized 90% of the world's natural rubber supply. Every tree, every plantation, every warehouse full of raw latex, every processing facility, gone. Cut off from the Allied world as completely as if the rubber had never existed. The United States consumed roughly 800,000 long tons of natural rubber per year. It produced none. It grew none. Every ounce came from trees that now stood behind Japanese lines. The stockpile, the strategic reserve that the Rubber Reserve Company had frantically accumulated since 1940, contained roughly 630,000 tons. That was less than 1 year's peacetime consumption. In wartime, with the military demanding tires for trucks, tanks, aircraft, jeeps, and the million other vehicles that a mechanized army required, the stockpile would be exhausted in months. Without rubber, no vehicle could move, no airplane could land, no tank could roll, no ship could seal its hatches or dampen its vibrations. Without rubber, the United States of America could not fight a war. And in February 1942, the United States had no synthetic alternative that worked. This was not a shortage. This was an existential crisis, more urgent, some historians have argued, than the development of the atomic bomb. Without the bomb, America would have won the war eventually, at a greater cost. Without rubber, America might have lost it. Rubber is not a simple material. It is a miracle of molecular engineering that nature spent millions of years perfecting, and that human chemists spent decades trying to replicate. Natural rubber is polyisoprene, a polymer, a long chain of isoprene molecules linked together in a specific geometric arrangement called cis-1,4 configuration. This arrangement gives natural rubber its defining properties: elasticity, resilience, tensile strength, resistance to abrasion, and the ability to flex millions of times without cracking. A tire made of natural rubber can deform under load, absorb shock, grip a wet road, and return to its original shape millions of times, over tens of thousands of miles, without failure. No synthetic material in 1942 could do all of this. The gap between natural rubber and the best available synthetic was not a matter of degree, it was a matter of kind. The synthetic rubbers that existed, Buna S, neoprene, thiacol, were useful for specific applications. Neoprene, developed by DuPont, was excellent for gaskets, hoses, and chemical-resistant coatings. Thiacol was used for fuel tank liners, but none of them could make a tire that would survive the service conditions that military vehicles demanded. Heavy loads, rough terrain, extreme temperatures, sustained high speed, and the constant flexing that turns rubber to heat and heat to failure. The German chemical industry had been working on synthetic rubber since the 1930s, driven by the same strategic logic that would later drive the American program. Germany had no natural rubber supply of its own, and the British naval blockade of World War I had demonstrated how quickly a nation could be strangled by the loss of imported raw materials. IG Farben, the German chemical conglomerate, developed Buna rubber, a synthetic made from butadiene and sodium, natrium in German, hence Buna. Buna S, which added styrene to the formula, was the variant that showed the most promise for tire production. Germany was producing Buna S in significant quantities by 1940, though the quality remained inferior to natural rubber for many applications. The Americans knew about Buna S. Standard Oil of New Jersey had a pre-war technology sharing agreement with IG Farben that included access to the Buna process. But the agreement was controversial. It would later become the subject of antitrust investigations and Senate hearings, and the practical knowledge transferred was incomplete. The Americans had the chemistry. What they lacked was the industrial infrastructure to produce synthetic rubber at the scale the war demanded. The scale was staggering. In 1941, the United States produced approximately 8,000 tons of synthetic rubber. The war required roughly 800,000 tons per year. The deficit, the gap between what America could make and what it needed, was a factor of 100. Closing that gap meant building an entirely new chemical industry from nothing in the middle of a war, using processes that had never been tested at production scale, with feedstocks that were themselves in short supply. The feedstock problem was critical. Buna S rubber is made from two raw materials, butadiene and styrene. Butadiene can be produced from petroleum or from grain alcohol. Styrene comes from petroleum. Both require large-scale chemical processing facilities, cracking towers, distillation columns, polymerization reactors that did not exist in 1942 and had to be designed, built, and commissioned in months rather than years. Roosevelt appointed a rubber survey committee in August 1942 to cut through the bureaucratic confusion that had paralyzed the synthetic rubber program during its first critical months. The confusion was real and damaging. Multiple government agencies, the War Production Board, the Rubber Reserve Company, the Office of the Petroleum Coordinator, the Board of Economic Warfare, each claimed authority over some aspect of the rubber problem, and their overlapping jurisdictions produced turf wars that consumed time the nation did not have. The petroleum industry wanted to make butadiene from oil. The agricultural lobby wanted to make it from grain alcohol, a process that would benefit Midwestern farmers. Standard Oil of New Jersey was pushing its own patented process, which raised questions about the pre-war technology sharing agreement with IG Farben and whether Standard Oil had deliberately delayed American synthetic rubber development to protect its German partners' interests. The committee was chaired by Bernard Baruch, the financier and presidential advisor who had served as chairman of the War Industries Board in the First World War and who at 72 brought both credibility and impatience to the task. James B. Conant, the president of Harvard, and Carl T. Compton, the president of MIT, provided the scientific authority. The Baruch Committee's report, delivered in September 1942, was blunt to the point of brutality. The rubber situation was so dangerous that unless corrective measures are taken immediately, this country will face both a military and civilian collapse. The committee recommended an immediate crash program to build 51 synthetic rubber plants, to be financed by the government through the Defense Plant Corporation and operated by private industry under contract. It recommended that a single rubber director, with authority over all agencies involved in rubber, be appointed to eliminate the bureaucratic warfare. William Jeffers, the president of the Union Pacific Railroad, was appointed to the position in September 1942. Jeffers was a railroader, not a chemist. He knew nothing about polymerization. What he knew was how to manage a large, complex organization and how to tell powerful men that their preferences were irrelevant. He cut through the turf wars with the force of a locomotive. He told the petroleum industry to build butadiene plants. He told the agricultural lobby they would get their alcohol to butadiene plants too. He told Standard Oil to stop arguing about patents and start producing rubber. He told everyone that the deadline was not negotiable. The plants were built. The speed of construction rivaled the Liberty Ship program in its urgency and exceeded it in chemical complexity. Each plant was a maze of towers, pipes, reactors, and tanks, a small chemical refinery, designed from blueprint to operation in months. By 1944, more than 50 factories across the United States, in Texas, Louisiana, Ohio, West Virginia, Kentucky, California, and a dozen other states, were producing GRS at a combined rate that approached 800,000 tons per year. The chemistry of GRS production was an industrial achievement that deserves more recognition than it has received. The process began with butadiene, a gaseous hydrocarbon that, at room temperature, is a colorless gas with a faintly aromatic smell. Butadiene was produced by two methods, from petroleum through the catalytic dehydrogenation of butane and butylene, and from grain alcohol through a process developed by the Russian chemist Sergei Lebedev in the 1920s and adapted for industrial use by the Carbide and Carbon Chemicals Corporation. The petroleum route was more efficient, but the grain alcohol route was pursued simultaneously because petroleum was itself a strategic material in short supply, and the grain-producing capacity of the American Midwest was, for all practical purposes, unlimited. The butadiene was then combined with styrene in a polymerization reactor, a large vessel in which the two monomers were mixed in an emulsion with water, soap, and a chemical initiator that triggered the linking of the molecules into long polymer chains. The polymerization was carried out at a controlled temperature, roughly 50 degrees Celsius, for 12 to 14 hours. The result was a latex, a milky suspension of synthetic rubber particles in water that was then coagulated, washed, dried, and pressed into bales for shipment to tire factories. The tire factories, Goodyear, Firestone, B.F. Goodrich, U.S. Rubber, received the GRS bales and compounded them with carbon black, sulfur, zinc oxide, and other additives to produce a material that could be molded into tires. The compounding was critical. Raw GRS was inferior to natural rubber in nearly every measurable property. It was weaker, less elastic, less resistant to heat buildup, and more prone to cracking. The additives, particularly carbon black, which was produced by the incomplete combustion of natural gas, improved the properties dramatically. A GRS tire compounded with 30% carbon black was still not as good as a natural rubber tire, but it was good enough to roll, good enough to fight. The carbon black industry itself had to be massively expanded. Before the war, carbon black was a niche product used primarily in printing inks and paint. The synthetic rubber program consumed carbon black in quantities that dwarfed all previous demand. New carbon black plants were built across the oil-producing regions of Texas, Louisiana, and Oklahoma, burning natural gas to produce the fine, powdery black material that gave synthetic rubber tires their strength and their characteristic color. The workers who operated the new synthetic rubber plants were, like so much of the wartime workforce, people who had never worked in chemical manufacturing before. The plants were dangerous. Butadiene is a known carcinogen, though this was not fully understood in the 1940s. Styrene is toxic in high concentrations. The polymerization reactors operated at pressures and temperatures that, if mismanaged, could produce runaway reactions. The carbon black plants, where natural gas was burned in enormous furnaces under controlled conditions, operated in an environment of soot and heat that coated every surface and every lung. The plants ran around the clock, 3 shifts, 7 days a week. The workers, many of them women, many of them recruited from agricultural communities in Texas and Louisiana, learned to monitor the reactor temperatures, adjust the emulsion chemistry, test the polymer output, and maintain the equipment that converted raw petroleum fractions into the rubbery sheets that were baled and shipped to the tire factories. They were chemical workers by necessity, not by training. The learning curve was steep, the errors were costly, and the margin between a successful batch and a failed one was measured in degrees of temperature and fractions of a percentage in the monomer ratio. On the battlefield, the rubber crisis manifested in ways that most histories of the war never mention. In North Africa in 1942 and 1943, American trucks and jeeps wore out their tires at rates that shocked the supply officers. The desert sand, abrasive, hot, unforgiving, ground through tire treads in hundreds of miles instead of thousands. The replacement tires, when they arrived, were often recapped, worn casings with a thin layer of new rubber applied to the tread surface. Recapped tires on a 2.5-ton truck carrying ammunition across the Sahara lasted days, not weeks. Blowouts were constant. Every blown tire was a truck stopped, a convoy delayed, supplies that did not reach the front. In the Pacific, the heat was worse than the sand. Rubber that sat in the tropical sun softened, degraded, and lost its resilience. Tires on aircraft, which absorbed enormous heat during takeoff and landing, required the highest quality natural rubber, and natural rubber was exactly what was in shortest supply. The Army Air Forces competed with the ground forces for tire allocations, and the tire allocation system became one of the most contentious supply disputes of the war. Fighter planes needed tires, bombers needed tires, trucks needed tires, jeeps needed tires, tanks needed rubber track pads, artillery pieces needed rubber-tired wheels for highway transport. The entire American military machine ran on rubber, and there was not enough of it. The situation was dire enough that the Army experimented with steel wheels on some vehicles, a reversion to pre-pneumatic technology that reduced mobility, increased vibration damage to cargo and equipment, and destroyed roads. The experiments were abandoned. There was no substitute for rubber. There was no workaround. There was only the desperate hope that the synthetic rubber plants would come online before the stockpile ran out. They did. Barely. While the chemical plants were being built, the country was running out of rubber. The rationing program that the government imposed in 1942 was the most restrictive and most unpopular civilian conservation measure of the war. Tire rationing began on January 5, 1942, less than a month after Pearl Harbor, before the synthetic rubber plants had even been designed. New tires were unavailable to civilians. Used tires were rationed. Recapped tires, worn tires with a thin layer of new rubber applied to the tread surface, became the only option for most American drivers. Gasoline rationing followed, not because there was a shortage of gasoline, but because rationing gasoline was the most effective way to reduce tire wear. A car that drove fewer miles wore out its tires more slowly. The A, B, and C ration stickers that appeared on every American windshield were not primarily about fuel conservation. They were about rubber conservation. The entire gasoline rationing system, the stickers, the ration books, the inspection stations where officials checked tire condition before issuing additional fuel coupons, was a vast nationwide program designed to keep 4 tires on every car long enough for the synthetic rubber plants to come online. Roosevelt launched a national scrap rubber drive in June 1942, asking every American to contribute old tires, rubber boots, garden hoses, rubber balls, bathing caps, and anything else made of rubber to collection points across the country. The response was enormous. Over 450,000 tons of scrap rubber were collected in a matter of weeks. Much of it was unusable, contaminated with fabric, metal, or dirt, degraded by age and weather. But the fraction that could be reclaimed was processed and blended with the dwindling supply of virgin rubber to stretch the stockpile as far as possible. The 35-mile-per-hour national speed limit, imposed in 1942 and maintained for the duration of the war, was another rubber conservation measure. Higher speeds generate more heat in a tire, and heat is the enemy of rubber. At 35 miles per hour, a tire lasted roughly twice as long as it did at 60. The speed limit saved tires, the tires saved rubber, the rubber saved the war. There were stranger attempts, too. The government funded research into guayule, a small woody shrub native to the deserts of northern Mexico and southwestern Texas that produces a natural latex similar to tree rubber. A guayule research program was established at the Manzanar War Relocation Center in California, the internment camp where Japanese Americans had been forcibly relocated. The cruel irony was not lost on anyone who paused to consider it. American citizens of Japanese descent, imprisoned because of their ancestry, were put to work growing rubber plants to replace the rubber supply that Japan had captured. The Guayule program produced useful research but never achieved production-scale output. The chemistry of synthetic rubber was faster than the biology of desert shrubs. The synthetic rubber that emerged from the wartime factories was not as good as natural rubber. Everyone knew this. The tire companies knew it, the military knew it, the drivers who put GRS tires on their cars and trucks and found them harder, louder, and less durable than the natural rubber tires they replaced knew it. But the synthetic had advantages that natural rubber did not. It was consistent. Every batch from every factory met the same specification, which was not always true of natural rubber, whose quality varied by plantation, season, and processing method. It was available, produced from petroleum and grain that America had in abundance, rather than from trees on the other side of an ocean controlled by the enemy. And it was improvable. Each generation of GRS was slightly better than the last, as the chemists and engineers who operated the plants refined the polymerization process, improved the emulsion recipes, and developed better compounding techniques. By the end of the war, GRS tires were approaching the performance of natural rubber tires for most applications. They were still inferior for aircraft tires. The extreme heat generated by landing gear touchdown required the superior heat resistance of natural rubber, and for some specialized military applications. But for trucks, jeeps, tanks, and the millions of civilian automobiles that would need tires when the war ended, GRS was adequate. More than adequate. It was the future. The Germans, who had started earlier and invested more heavily in synthetic rubber than any other nation, found that their Buna program could not keep pace with American production. The irony was savage. Germany had been the pioneer of synthetic rubber. IG Farben had developed the Buna process in the 1930s, had built the first production-scale plants, had supplied the Wehrmacht with synthetic tires for the invasion of Poland, France, and the Soviet Union. But German production peaked at roughly 130,000 tons per year. Impressive for a nation under blockade, but a fraction of the American output. By 1944, Allied bombing of the IG Farben synthetic rubber plants, particularly the massive facility at Auschwitz III, Monowitz, was reducing German synthetic rubber output at precisely the moment when Germany's military needed it most. The Monowitz plant, built at a cost of over 900 million Reichsmarks, was intended to produce 30,000 tons of Buna rubber per year. It never reached its design capacity. The workforce was drawn primarily from the Auschwitz concentration complex. Prisoners who were selected for labor rather than immediate murder worked under conditions of starvation and brutality and died at rates that required a constant flow of replacements from the transports arriving daily at the Auschwitz railhead. The Monowitz plant was both an industrial facility and a death sentence. Of the approximately 35,000 prisoners who worked there during the war, at least 25,000 died. The plant's failure to reach production targets was a consequence not only of bombing, but of the fundamental insanity of using starved, brutalized slave labor to perform precision chemical manufacturing. Malnourished workers made errors. Beaten workers sabotaged equipment. Dying workers produced nothing. The Nazi regime's commitment to genocide and its commitment to industrial production were, in the end, contradictory goals. Monowitz proved that you cannot build an industrial economy on murder. The Americans proved that you can build one on persuasion, wages, and the energy of a free workforce. Japan had no synthetic rubber program of any consequence. Japan's seizure of Southeast Asia had given it access to all the natural rubber it needed, or so it seemed. In practice, Japan lacked the shipping to transport raw latex from the plantations to the home islands because American submarines were sinking Japanese merchant ships faster than Japan could build them. By 1944, the shipping routes between the Dutch East Indies and Japan were so dangerous that entire convoys were being lost. The rubber sat in warehouses in Malaya and Singapore, while Japan's military ran short of tires, gaskets, and every other rubber product that modern warfare required. The irony was complete. Japan had captured the rubber that America needed, but Japan could not use it either. The submarines that America powered with Fairbanks Morse diesels were destroying the shipping that carried the rubber that Japan had stolen. A circle of logistics that favored the nation with the larger industrial base and the longer reach. When the war ended, the synthetic rubber industry did not disappear. It transformed, and in transforming, it changed the global economy of raw materials in a way that no other wartime program matched. The 51 government-owned plants were operated by private companies: Goodyear, Firestone, Standard Oil, Phillips Petroleum, Dow Chemical, and others, under cost-plus contracts that guaranteed the operators a profit regardless of efficiency. After the war, Congress debated whether to sell the plants to the operators, retain them in government ownership, or shut them down entirely. The debate was heated. Liberals argued that the plants should remain in government hands as a check on rubber industry monopoly power. Conservatives argued that government ownership of industrial facilities was socialism by another name. The tire companies, who had learned to work with GRS and had no desire to return to total dependence on imported natural rubber, lobbied for privatization. The Rubber Act of 1948 kept the plants in government hands temporarily, and the rubber industry continued to produce GRS under government supervision. In 1950, the Korean War created a new surge in demand that justified continued operation. Finally, in 1955, the Rubber Producing Facilities Disposal Act authorized the sale of the plants to the private sector. The government's synthetic rubber program, born in crisis, sustained by war, and maintained by the Cold War, was privatized 13 years after it began. The total investment had exceeded $700 million in 1940s money, roughly $10 billion in today's dollars. It was the most expensive government-directed industrial program of the war after the Manhattan Project. By then, synthetic rubber had surpassed natural rubber in global production volume. The material that had been an emergency substitute, a wartime expedient, accepted only because the alternative was losing the war, had become the dominant form of rubber on Earth. Today, roughly 70% of all rubber produced worldwide is synthetic. The tires on your car are synthetic. The belts in your engine are synthetic. The seals in your plumbing, the gaskets in your appliances, the soles of your shoes, synthetic. The world runs on synthetic rubber, and synthetic rubber exists at this scale because Japan captured Singapore in February 1942, and the United States, facing the loss of a material it could not do without, invented an industry in 2 years that would outlast the war by 8 decades and counting. The chemistry has improved beyond recognition. Modern synthetic rubbers, EPDM, silicone, nitrile, butyl, and dozens of other formulations are engineered for specific applications with properties that natural rubber cannot match. Heat resistance, chemical resistance, ozone resistance, low temperature flexibility. Each synthetic is tailored to its task with a precision that the wartime GRS chemists could only dream of. But the foundation was laid in 1942 by chemists and engineers working under a deadline measured not in quarters or fiscal years, but in months before the stockpile ran out. They built 51 factories. They produced 800,000 tons per year. They replaced a natural material that had taken millions of years to evolve with a synthetic material that took 2 years to industrialize. They did it because the alternative was not having tires, and not having tires meant not having a war, and not having a war meant not having a country. 3,700 tons of synthetic rubber in 1942, 756,000 tons in 1945, a 200-fold increase in 3 years, from a standing start to the largest chemical manufacturing program in American history, built from scratch in the middle of a global war using chemistry that had barely left the laboratory. That is how America got its rubber. Not from trees, from petroleum, from grain alcohol, from carbon black, from chemistry, from desperation and from the refusal to accept that a war could be lost because of a material that grows on a tree 10,000 miles away. The trees are still there, the plantations still produce, but the world no longer depends on them because 60 years of American engineers and chemists building on the foundation that the wartime program laid made the tree optional. The tire on your car does not contain a single molecule of natural rubber. It is entirely synthetic. And it exists because Singapore fell and America had to invent its way out of a crisis that no one had prepared for and everyone should have seen coming.